As the globe rejoins in relief over Three-Eye Atlas, the third traveler of the stars in recorded history, a more disquieting event is stealthily taking shape, and it has only just come to our attention. A comet, erupting with activity, is venturing perilously close to Earth's path. It eluded our instruments until the very sun inadvertently revealed its presence. On October 30th, 2025, a mere 8 days from now, it will achieve its closest proximity to our planet. What does this portend for us here on Earth? Is this the genuine peril? Remain with me until the conclusion, and you will understand why the actual threat was never the comet dominating headlines, but rather the one we almost failed to detect at all. If these enigmas captivate you as they have me, be sure to click like and subscribe to ensure you don't miss any updates as this narrative unfolds in real time. Share your location in the comments, along with the current time there, and whether you believe we are receiving the complete picture concerning these world-altering revelations. Furthermore, if you wish to aid this community in its expansion, disseminate this video across X, Facebook, Reddit, or even within your personal group conversations. Your support is the very reason we can continue to pursue stories of this nature. Therefore, thank you for standing by us. Part 1. The immediate focus. The entirety of the world's attention is fixed on 3 Atlas. The media hails it as enigmatic, social platforms buzz with speculation, and astronomers are going to great lengths to assure us of its harmlessness. And they are correct. 3 Atlas, that celestial voyager from beyond our solar vicinity, will traverse past Earth at a comfortable distance of 1.8 astronomical units, equivalent to approximately 167 million kilometers. NASA has stated it unequivocally. No danger. Its trajectory remains well clear of ours, a mere cosmic observer destined to glide by and recede into the vast unknown. So, what fuels our fascination with it? Because it originated from elsewhere, because the word interstellar carries a certain mystique that causes us to overlook practical concerns. We are enamored with the extraordinary visitor, the stranger at our doorstep. We neglect to consider who might already be within our abode. While the world's gaze is upon 3 Atlas, another entity is subtly encroaching into our celestial neighborhood. Comet C-2025R2, named Swan after the instrument that identified it, is drawing nearer. On October 30th, 2025, just 8 days from now, it will reach its closest point to Earth. Not 1.8 astronomical units, not even one. 0.2606 astronomical units, approximately 39 million kilometers. This is closer than one might imagine. This is closer than we typically permit unexpected guests to approach. Allow me to provide you with the details of this phenomenon. R2 was detected in late September of 2025 by an amateur astronomer named Vladimir Bazugi. He was not employing a telescope. Rather, he was examining data from a solar wind instrument aboard the SOHO spacecraft, observing the fluorescence of hydrogen emissions in ultraviolet light. This is an atypical method for discovering comets. Typically, ground-based optical surveys meticulously scan the sky, identifying faint points of reflected sunlight. However, R2 remained imperceptible to them. It had been concealed within the sun's glare, its angular proximity too great for terrestrial telescopes to discern. This phenomenon is referred to as the Huligtek or Hulich blind spot effect. Celestial bodies within this region are akin to phantoms. They exist, yet we cannot perceive them until they emerge from this obscuration. R2 only became visible after it had already completed its perihelion passage, its closest approach to the Sun, on September 12, 2025. By the time we became aware of it, it was already on its outward trajectory, heading in our direction. Its perihelion distance was approximately zero point 0.5 astronomical units, about 75 million kilometers from the Sun. This proximity is sufficient to vaporize volatile materials from its surface, triggering outbursts and destabilizing its structure. And indeed, it did. In late September, observers documented a sudden surge in brightness. The comet's magnitude increased to approximately 5.9 or 5.6, depending on the report. Its coma, the diffuse envelope of gas and dust surrounding the nucleus, expanded significantly. Photographs revealed a greenish aura, indicative of diatomic carbon and cyanogen radicals, fluorescing under solar ultraviolet radiation. Its tail extended across several degrees of the sky, discernible through binoculars if one knew precisely where to direct their gaze. However, here lies the crucial point. We still lack knowledge of the nucleus's dimensions. We are unaware of its rotational state. We cannot ascertain if it has undergone fragmentation or if it is poised to do so. Comets are inherently volatile bodies. They are prone to shedding fragments, fracturing into pieces, and dispersing debris fields along their orbital paths. Should R2 exhibit any of these behaviors, its fragments will deviate slightly from the parent object's trajectory. They will disperse, forming a nebulous cloud of potential intersections with Earth's orbital path. The minimum orbit intersection distance, or MOD, between R2 and Earth is approximately 0.048 astronomical units. This translates to about 7 million kilometers. In astronomical terms, this is an infinitesimal gap, the narrow boundary between safety and potential peril, contingent upon subsequent events. Now, I am not suggesting that R2 is destined to collide with us. Current orbital calculations indicate this will not occur. However, I contend that our incapacity to detect it sooner represents the genuine hazard. We have engineered a detection system that functions admirably for objects situated in the appropriate celestial regions, exhibiting suitable luminosity, and arriving at the opportune moment. Yet, if an object remains concealed within the sun's brilliance, arrives from an unexpected vector, or experiences a sudden increase in luminosity after we have ceased our observations, we fail to detect it. We overlooked R2 until it was virtually upon us. How many others have we missed entirely? This discussion is not intended to incite panic. Panic is unproductive. It is about cultivating vigilance regarding that which perpetually evades our scrutiny. It is about recognizing that the most alarming celestial bodies are not those gracing our headlines, but rather those we fail to perceive until it is too late. 3A Atlas serves as a diversion, the magician's flourish designed to distract while the true spectacle unfolds elsewhere. R2 is the actual spectacle. Therefore, here is our plan. First, we will deconstruct the 3I Atlas distraction, demonstrating its inherent safety. Subsequently, we will delve into all that we know and all that remains unknown about R2. We will examine speculative risk scenarios, including dust trails, fragments, and meteoroid swarms. We will contrast this with prior near misses that were barely detected, objects that skirted our defenses with mere days or hours of warning. And finally, we will outline what you should be observing, what you should demand from the institutions tasked with monitoring these phenomena, and what transpires when the detection system falters, as it does more frequently than one might assume. And when that occurs, the entity that slips through may not be the one we were anticipating. Part 2. The Mechanics of Discovery. Why did Swan detect it, and ground surveys fail? Comets are typically identified through optical sky surveys. Telescopes meticulously scan the night sky, searching for faint points of light that shift against the backdrop of distant stars. These points grow brighter as they approach the sun, their ice sublimes, and they develop tails. This methodology has been employed for centuries and is generally reliable, with notable exceptions. Comet C2025R2 was not discovered by an optical telescope. Its identification was made by a hydrogen emission detector aboard a spacecraft in solar orbit. This instrument is named SWAN, an acronym for Solar Wind Anisotropies, and is an integral component of the SOHO mission, the Solar and Heliospheric Observatory, launched in 1995. SWAN was engineered to image the solar wind by detecting hydrogen's Lyman alpha emissions within the ultraviolet spectrum. Hydrogen emits at a specific wavelength, 12 1.6 nanometers, imperceptible to the human eye but highly visible in ultraviolet light. When comets release water vapor through sublimation, this vapor dissociates into hydrogen and oxygen. The hydrogen then disperses to form an immense cloud surrounding the comet, far exceeding the dimensions of the visible coma. SWAN possesses the capability to observe this cloud from millions of kilometers away, even when optical telescopes detect nothing. This is not an unprecedented technique. SOHO SWAN has been responsible for discovering thousands of comets throughout its operational tenure. The majority of these have been small, sun-grazing objects that plunge into the solar atmosphere and subsequently vaporize. However, R2 is not a sun grazer. It is an interplanetary visitor, likely originating from the Oort cloud, making a close pass by the sun before embarking on its return journey to the outer reaches of the solar system. Its invisibility to ground surveys was a consequence of its position. It was too proximate to the sun in the sky, with an insufficient angular separation. Telescopes situated on Earth are incapable of observing the sun directly without sustaining damage. Consequently, there exists a zone encircling the sun, a cone of obscured vision, wherein objects effectively vanish from our perception. Astronomers refer to this as the Hulegtek effect, or the Hulich blind spot, depending on the preferred historical attribution. The underlying principle remains consistent. Objects within this zone are effectively spectral, existing but undetectable. R2 traversed this zone during its perihelion passage. It circumnavigated the Sun on September 12, 2025, at a distance of approximately 0.5 astronomical units, roughly 75 million kilometers. For several weeks preceding and following this event, it remained beyond the reach of optical surveys. By the time it emerged from the sun's glare, it had already completed its closest approach to the sun and was progressing outward, heading towards Earth's orbital vicinity. It was at this juncture that Vladimir Bezugi, an amateur astronomer, identified it in the SWAN data. He was meticulously reviewing archived ultraviolet imagery, searching for the distinctive luminescence of hydrogen. He detected a discernible mass, a diffuse cloud that shifted its position over time. He flagged his observation. Subsequent investigations by other observers ensued, culminating in optical confirmation. The comet was authenticated. Nevertheless, by this point, weeks of crucial observation time had been forfeited. We lacked any data regarding its pre-perihelion activity. We were unaware of its rate of brightening, the evolution of its trajectory, or whether it had already commenced fragmenting. Detection bias operates as a severe impediment. Optical surveys are subject to limitations concerning minimum observable magnitudes, gaps in sky coverage, interruptions due to weather, and zones of obscuration caused by solar glare. Hydrogen ultraviolet instruments like SWAN possess distinct sensitivities and different blind spots. While they can detect comets that elude optical telescopes, they are not engineered for comprehensive sky surveys. They are specialized instruments, and specialized instruments identify specialized phenomena. The ramifications of delayed detection are significant. Orbital uncertainties are amplified when observational data is scarce. Extended periods are requisite for refining trajectories, measuring orbital perturbations, and accounting for non-gravitational forces such as outgassing. R2 was identified belatedly, rendering its orbit uncertain. Even now, weeks later, margins of error persist. We have a general understanding of its path, but general is not synonymous with precise. In the realm of orbital mechanics, precision is paramount. Furthermore, we miss the initial stages of its activity. Comets frequently experience outbursts in close proximity to the Sun, when solar heating triggers explosive releases of volatile compounds. If R2 underwent such an event, it went unobserved by us. We cannot determine if it shed substantial fragments during that period. We are ignorant of whether its nucleus sustained fractures. We do not know its rotational state, which influences its spinning and wobbling motions under the influence of asymmetric outgassing forces. All of this vital information is irretrievably lost. We are attempting to predict the behavior of an object whose performance we only began observing midway through its spectacle, effectively flying blind. This situation is not attributable to individual shortcomings of astronomers, but rather represents a systemic limitation within our detection network. We have optimized our capabilities for specific types of celestial bodies situated in particular regions of the sky. When an object deviates from these parameters, we fail to detect it, and we miss it entirely until an amateur astronomer, granted access to spacecraft instrumentation, happens upon a hydrogen glow in archived data. How many other comets have gone unnoticed? How many are presently traversing our solar system, invisible due to their unfavorable positioning or unfortunate timing? We lack this knowledge. We are incapable of acquiring it. This is the fundamental issue. In the subsequent segment, we will examine the actual observed activities of R2 since its discovery, the outbursts, the anomalies, and the structural peculiarities that elevate this comet beyond a mere icy celestial body. Part 3. The Observed Actions of R2. Allow me to guide you through the timeline. On September 11th, 2025, Vladimir Bazougi identified a moving hydrogen source within the SWAN imagery. The object was assigned the designation C2025R2, with the R signifying the latter half of the month of discovery, and the 2 indicating it was the second comet identified during that period. Optical confirmation followed swiftly. Ground-based observers directed their telescopes toward the recorded coordinates and observed it. A nebulous patch, a coma faintly illuminated in the pre-dawn sky. The comet had completed its perihelion passage the preceding day, on September 12th, at a solar distance of approximately 0.50347 astronomical units. This is an exceptionally close proximity. It is sufficiently near to sublimate water ice, carbon dioxide, methane, and ammonia, all the volatile substances carried by comets. It is close enough to instigate activity, and activity did manifest in late September. Observers reported a sudden increase in brightness. The comet's apparent magnitude surged, with some estimations placing it at 5.9, while others indicated 5.6. Magnitude is a logarithmic scale, meaning even a minor numerical adjustment signifies a substantial augmentation in luminosity. The coma underwent expansion. Photographic evidence displayed a greenish halo encircling the nucleus, a characteristic signature of diatomic carbon molecules fluorescing under ultraviolet radiation. This phenomenon is not uncommon in comets. Carbon compounds sublimate from the nucleus, undergo ionization by solar radiation, and emit a green glow. While it may appear exotic, it is simply a manifestation of chemical processes. The comet's tail exhibited asymmetries. Certain images revealed distinct streamers, narrow jets of material emanating away from the sun. This suggests localized outgassing, likely originating from active vents on the nucleus's surface. Comets are not uniform entities. They are composites of ice and rock, with certain regions possessing a higher concentration of volatiles than others. As the nucleus rotates, different vents are exposed to the sun, triggering intermittent bursts of activity. The resulting tail displays variability in shape, pulsates, and occasionally bifurcates into multiple streams. R2 displayed all of these characteristics. Observers also noted significant dust retention. Ordinarily, solar radiation pressure propels small dust particles away from the comet, forming a smooth tail. However, if these particles are substantial in size or possess adhesive properties, they lag behind, creating a diffuse cloud that disperses gradually. R2 appeared to be generating a considerable volume of larger dust particles. This has significant implications. The presence of large dust particles suggests the nucleus is shedding material, potentially fragments, or pieces of its surface fracturing under thermal stress. If these fragments are sufficiently large, they may persist as independent objects, each following its own trajectory, and these trajectories could diverge from that of the parent comet, thus creating a debris field that spans across space. One particularly striking image was featured on the Astronomy Picture of the Day website on September 18, 2025. It depicted R2's greenish coma against the twilight sky, with its tail extending upward, away from the brilliance of the obscured sun. The comet was still positioned low on the horizon, presenting observational challenges, yet it was undeniably visible. Astrophotographers successfully captured it, some utilizing binoculars, others employing small telescopes. Reports describe the tail as extending for several degrees, a spectral ribbon unfurling across the sky. However, the crucial point is this: brightness predictions for comets are notoriously imprecise. Comets do not adhere to predictable patterns. They exhibit outbursts, they diminish in brightness, they fragment. Their luminosity is contingent upon the extent of actively sublimating surface area, which, in turn, depends on the nucleus's size, composition, rotation, and the intensity of solar heating. While we can formulate educated estimations, comets possess an inclination for surprising us. Predictions indicated that R2 would attain a magnitude of 4 under optimal conditions, rendering it readily visible to the naked eye from a location with minimal light pollution. Other forecasts are more conservative, suggesting it would remain around magnitude 6, necessitating the use of binoculars. As of October 20th, 2025, the reported magnitude is approximately 6.7, placing it just below the threshold for naked eye visibility. Whether it will further brighten hinges on the occurrence of additional outbursts, and we are uncertain if this will happen. The nucleus itself remains unresolvable. Telescopes can only discern the coma, the luminous envelope of gas and dust. The solid core is concealed within, too diminutive and faint to be distinguished. We do not know its precise dimensions. Estimates derived from brightness and activity data suggest a diameter on the order of a few kilometers, but this remains speculative. We are unaware of its shape. We cannot determine if it is a singular entity or a conglomerate of fragments loosely bound together. We do not know if it has already fractured. Certain comets undergo fragmentation discreetly, shedding pieces without dramatic outbursts. Their fragmentation becomes apparent only later, upon high-resolution imaging of the coma, revealing multiple condensations or nuclei. While speculative, this possibility warrants consideration. The outburst observed in late September indicates the presence of internal volatile reserves. A buildup of pressure within the comet led to a violent release. This could be attributed to carbon monoxide ice, which sublimates explosively. Alternatively, it might be subsurface pockets of water ice suddenly exposed to solar radiation. It could also be a structural failure, a fissure opening and venting gas. Regardless of the cause, it occurred once. It has the potential to recur. And if it transpires at an inopportune moment, when the comet is in close proximity to Earth, its fragmentation will result in the dissemination of debris, forming a cloud that we might traverse. Next, we will examine the numerical data, the precise orbital information, the distances, speeds, and geometrical configurations that determine whether this phenomenon is a matter of mere curiosity or genuine concern. Part 4. The concrete numbers and the orbital reality check. Allow me to present the geometrical specifics. Comet C2025R2 follows a trajectory around the Sun that is nearly parabolic. Its orbital eccentricity is 0.999369929, an exceptionally high value representing a near parabolic path. An eccentricity precisely equal to 1 signifies a parabola, an open curve indicating an object that originates from infinite distance and returns to it. An eccentricity slightly less than 1 describes an extremely elongated ellipse, a trajectory that requires tens of thousands of years to complete. The semi-major axis of R2's orbit is approximately 798 astronomical units. This signifies that the farthest point of its orbit, the aphelion, lies far beyond the Kuiper belt, deep within the Oort cloud. Its orbital period is estimated at 22,554 years. This comet last visited the inner solar system during the late Paleolithic era, a period when humans were creating cave paintings and hunting mammoths. The inclination of the orbit is approximately 4.4747 degrees. This represents the angle between the comet's orbital plane and the ecliptic, which is the plane of Earth's orbit. 4.47 degrees is considered a low inclination. Most comets originating from the Oort cloud approach at steep inclinations, descending from random angles. R2, however, is nearly coplanar with the planets. This characteristic simplifies the prediction of its trajectory, but it also means that it spends a greater duration in proximity to the ecliptic plane, wherein Earth orbits. This proximity elevates the probability of close encounters. Perihelion, the point of closest approach to the Sun, occurred on September 12, 2025, at a distance of 0.50347 astronomical units. This equates to approximately 75 million kilometers, situated just inside the orbit of Venus. At this distance, solar heating is exceptionally intense. Surface temperatures can ascend to several hundred degrees Celsius. Water ice undergoes rapid sublimation, and volatile compounds are released. The nucleus expels dust and gas at a prodigious rate. This is the period during which comets attain their greatest luminosity, becoming spectacular celestial events, but also their most unstable. We now proceed outward. R2 is receding from the Sun, but its trajectory intersects Earth's orbital path. On October 30th, 2025, the comet will reach its closest approach to Earth. The distance will be 0.26065 astronomical units, which translates to approximately 38,925,117 kilometers. This is roughly 100 times the distance to the Moon. In human terms, this may seem considerable. However, in cosmic terms, it constitutes a near miss. The critical metric, however, is the MOD, the minimum orbit intersection distance. This is the smallest conceivable separation between Earth's orbit and the comet's orbit, calculated geometrically without regard to timing. For R2, the MODI is approximately 0.048 astronomical units, roughly 7 million kilometers. This signifies that if one were to superimpose both orbital paths in space and measure the shortest distance between them, the result would be 7 million kilometers. This is the gap. If the comet and Earth were positioned differently in their orbits at the same time, this gap could be reduced to 0. However, this is not the case. The current orbital solution indicates that on October 30th, Earth and R2 will be separated by 39 million kilometers. The comet will pass by and we will remain safe. This is what the models and calculations indicate. NASA has not issued any cautionary alerts. There is no impact notification. So why is this discussion still ongoing? Because orbital solutions are inherently imperfect. They are derived from observational data, and observational data contains uncertainties. The more data points we accumulate, the more refined our understanding becomes. Yet R2 was identified relatively late in its trajectory. Our current observation set is not as comprehensive as we would prefer. While the comet's orbital path is reasonably well defined, it lacks absolute precision. Minor deviations, such as those caused by non-gravitational forces stemming from outgassing, shifts in the comet's rotational state, or changes in its mass distribution, can subtly alter its course. A deviation of a few thousand kilometers might be inconsequential for the primary nucleus, but it becomes significantly impactful if the comet has dispersed fragments. These fragments can diverge from the parent body. Should R2 experience fracturing or disintegration, the resulting pieces will possess slightly different velocities. Over time, these pieces will spread out along the orbital path, eventually forming a trail of debris. Larger fragments will exhibit less divergence. Smaller remnants, including dust and pebble-sized particles, can disperse widely. Should Earth traverse this debris stream, we would anticipate an increase in meteor activity, potentially escalating to a meteor storm or an even more severe event. As of October 20th, 2025, its current apparent magnitude is 6.7. This is fainter than initially projected, but not entirely unexpected, as comets naturally diminish in brightness as they recede from the Sun. The critical question remains whether R2 will undergo another outburst. A sudden increase in brightness would signify renewed activity, possibly involving fragmentation or the expulsion of additional volatiles, thereby altering the perceived risk. Visual aids are beneficial. Envision the Sun at the solar system's center. Earth's orbit is depicted as a circular path around it, spanning approximately 150 million kilometers in radius. R2 follows a highly elliptical orbit, originating from the outer solar system, swooping around the Sun, and then heading back into interstellar space. Although the orbital paths intersect, they do not coincide in time. The comet passes through the point of intersection in October, with Earth arriving at that same location several months later. This separation is both spatial and temporal. As long as these conditions persist, there is no immediate danger. However, comets are inherently unpredictable celestial bodies. They do not adhere to strict schedules. They can exhibit erratic movements, fracture, and shed debris, with these fragments deviating from the parent object's trajectory. They drift, disperse, and occasionally arrive at unexpected moments. Our subsequent discussion will explore the observational landscape, the public fascination, the diversions, and the influence of media coverage on public attention. Part 5 delves into the near-term observational theater, the act of viewing, media interplay, and the phenomenon of public distraction. October is proving to be a remarkably active celestial month. Comet R2 is approaching its closest proximity to Earth, with its peak visibility anticipated around October 30th. However, it is not the sole celestial spectacle. Comet C 2025 A6, also known as Lemon, is also intensifying in brightness and becoming observable in the northern hemisphere concurrently. The presence of two comets, both discernible to amateur astronomers and both reaching their closest approaches within days of each other, creates a remarkable celestial event. This rarity amplifies public interest and encourages skyward observation. Adding to this, we have the Orionid meteor shower. The Orionids typically reach their peak activity around October 30th to 21st each year, a period when Earth traverses the debris trail left by Comet Halley. Yes, Halley, the renowned comet with a periodicity of approximately 76 years. Even when Halley is distant, its residual dust and ice fragments persist along its orbit. Every October, Earth passes through this stream, resulting in particles impacting our atmosphere at speeds of 70 kilometers per second. These particles incinerate upon entry, generating luminous streaks we identify as meteors. The Orionids generally produce between 10 and 20 meteors per hour during their peak, though this number can occasionally be higher. While not classified as a major storm, its reliability is noteworthy. Therefore, on the night of October 30th, 2025, observers can expect to see two comets in the sky alongside a meteor shower at its zenith. The heavens will be particularly active. This celestial convergence will undoubtedly be mirrored by extensive media coverage. Astronomy enthusiasts will inundate social media platforms with photographs, and news outlets will feature stories about this astronomical display. This presents an ideal opportunity for public engagement with science. It also, however, creates a perfect environment for distraction. While the public's attention is captivated by the Orionids, while astrophotographers are busy documenting the two comets, and while headlines extol the beauty and wonder of the cosmos, the critical questions regarding Comet R2 may receive minimal consideration. How precise is our knowledge of R2's trajectory? What is the margin of error in its orbital calculations? Has it undergone fragmentation? Are we effectively tracking any resulting debris? What are the potential implications should an unforeseen event occur? The Washington Post reported on the dual comet sighting, noting that both R2 and Lemon would be observable through binoculars or small telescopes. Their coverage highlighted the rarity and visual appeal of witnessing two comets simultaneously. However, the proximity of R2 was not emphasized, nor was the concept of minimum orbit intersection distance, MOID, mentioned, nor was the risk of fragmentation discussed. This is not a critique of the reporting itself, but rather an observation on the inherent nature of public science communication, where captivating spectacles often take precedence over meticulous risk assessment. Furthermore, there is the ongoing fascination with 3 Atlas, the interstellar visitor, which continues to dominate headlines despite its projected closest approach being 1.8 astronomical units, a distance considered safe by all relevant metrics. Media outlets are drawn to 3E Atlas due to its enigmatic nature. Originating from another star system, its reported color varies between red and green depending on the observational data, and its apparent color shifts, which is an unusual characteristic for asteroids. This has fueled speculation regarding artificial origins, alien probes, or encoded messages within its trajectory. While such hypotheses are improbable, they are undeniably captivating and highly shareable. In contrast, R2, the closer celestial visitor with an uncertain orbit and a history of outburst activity, receives comparatively less prominent coverage. Its nature as a native solar system object, likely originating from the Oort cloud, renders it less exotic. It is not an interstellar traveler, merely another comet in the grand scheme of things. However, this classification is inaccurate. R2 is a comet that eluded detection until it was remarkably close, having remained obscured by the sun's glare, emerging only after its perihelion passage. It is a comet that may have fragmented and could potentially fragment further. Its MOID is a concerning 7 million kilometers, a relatively small gap. Public perception is largely driven by novelty. 3 Atlas embodies novelty, whereas R2 does not. Consequently, 3 Atlas garners widespread attention, relegating R2 to a mere footnote. Yet, footnotes can harbor significant implications and obscure crucial details. It is imperative to acknowledge behavioral caveats in this context. Comets are not reliable celestial performers. Their brightening and fading can be unpredictable, and they are prone to fragmentation without prior warning. Predictive models are essentially informed estimations based on past behavior, but each comet possesses unique characteristics. R2 might brighten to a magnitude of 4, becoming visible to the naked eye as a spectacular sight. Alternatively, it could fade to magnitude 8, disappearing from view. It might fragment into multiple pieces, creating a significant debris field, or it might exhibit no further activity and quietly recede into the outer solar system, fading from public memory within a year. These are all possibilities, and we lack definitive knowledge. What we do know is that there is no immediate impact alert. Current orbital calculations indicate that R2 will pass Earth at a distance of 39 million kilometers. This is insufficient for a direct collision, but it is close enough to pose other risks. It is close enough for potential interactions with debris, close enough to cause increases in meteor flux, and close enough that if the comet were to fragment unexpectedly, some of its pieces could be redirected onto Earth-crossing trajectories. This encapsulates the nature of cosmic risk. It is not a simple binary of safe or doomed, but rather a probabilistic and uncertain scenario layered with various contingencies. Our current detection systems, the network of telescopes and surveys we rely on for early warning, are not designed to manage such contingencies. They are optimized for tracking predictable objects on stable orbits. When unpredictable events occur, such as an object obscuring itself within the sun's glare, experiencing a sudden brightening, or shedding fragments, both the system and our response capabilities face significant challenges. In the next segment, we will delve deeper into past near-miss events, examining asteroids that passed Earth with minimal warning and the detection failures that, regrettably, occur more frequently than acknowledged. Part 6 presents case studies of asteroids discovered just before or after their close approaches to Earth. In early 2025, an asteroid designated 2025 TF passed within approximately 400 kilometers of Earth's surface. 400 kilometers is closer than the International Space Station orbits, closer than most satellites, and within the operational altitudes of numerous space assets. We did not detect its approach until it was remarkably close. 2025 TF is a small object, estimated to be only a few meters in diameter. At this size, even if it had entered the atmosphere, it would have disintegrated, producing a brilliant fireball but causing no direct damage to the ground. The Chelyabinsk meteor event in 2013, involving an object estimated to be between 17 and 20 meters in diameter, exploded in the atmosphere with a force equivalent to several hundred kilotons of TNT. This event shattered windows and injured over 1,000 people, though it did not create a crater. 2025 TF, being smaller, would have presented a visual spectacle, nothing more. The crucial point, however, is not its size, but the latency in its detection. It remained undetected until it was virtually upon us. Its trajectory took it over Antarctica, one of Earth's most remote regions, where very few observers were present. Had its arrival been a few hours earlier or later, or had its trajectory been marginally different, it might have passed over a populated area, leaving us with no prior warning. This is not an isolated incident. In recent years, several small asteroids have been identified only days, hours, or even minutes before their closest approach to Earth. Some were confirmed only after they had already passed by. They navigated past Earth undetected by our observational surveys, and we only registered their presence on their outward journey. This phenomenon is a direct consequence of the limitations inherent in our detection network. Telescopes possess minimum brightness thresholds, and small objects, being faint, can easily fall below these thresholds. If an object approaches from the direction of the sun, it becomes invisible. If it travels at high velocity, it crosses the sky too rapidly for automated survey systems to capture. Objects with low albedo, meaning they reflect very little sunlight, blend seamlessly into the background, further hindering detection. This detection bias is not merely a theoretical concern, it is a demonstrable operational failure mode. We fail to detect numerous objects, often only realizing our oversight when an observer coincidentally directs their attention to the correct celestial region at the opportune moment and notices an anomaly. The implications of these missed detections are more profound than might initially be assumed. While most small asteroids disintegrate harmlessly in the atmosphere, not all do. Even a relatively small object can inflict catastrophic damage if it strikes a critical target. A few meters of rocky material impacting a satellite at orbital velocity would result in its immediate destruction. A collision with the International Space Station would have fatal consequences. An impact on a city, even from a modest-sized object, could devastate buildings and claim thousands of lives. While the atmosphere provides a shield, it is not an infallible one. Objects exceeding approximately 20 meters in diameter can survive atmospheric entry and reach the ground. Even smaller objects can generate destructive airbursts. Furthermore, the issue of debris must be considered. When an asteroid disintegrates within the atmosphere, it scatters fragments across a considerable area. Although most fragments are small, some can be substantial enough to cause damage. If the breakup occurs over a densely populated region, these fragments transform into dangerous projectiles. The Chelyabinsk event, for instance, scattered meteorites over hundreds of square kilometers, which people subsequently collected as souvenirs. However, had the object been larger, or had the disintegration occurred at a lower altitude, the resulting fragments would have posed a far greater hazard. Now, let us scale this scenario. Instead of a solitary small asteroid, envision a cloud of debris originating from a fragmenting comet. Instead of a few meters of rock, imagine hundreds or thousands of pieces, ranging from dust particles to sizable boulders, dispersed along the comet's orbital path. Rather than a single point of impact, we face a diffuse threat, a statistical hazard where the probability of any individual piece causing harm is low. However, the cumulative probability becomes non-negligible. This is the outcome when comets fragment. They do not unleash a single projectile, but rather a wide dispersal, akin to a shotgun blast. R2 possesses a minimum orbit intersection distance, MOID, of 7 million kilometers. This represents the closest proximity between Earth's orbital path and the comet's orbit. If the comet fragments and its constituent pieces disperse along its orbital path, some of these fragments might drift closer to Earth's trajectory, not to the point of zero separation, nor to impact, but sufficiently close to alter the statistical probability. This shift from negligible to a small but non-zero probability is enough to cause considerable concern among risk analysts. This serves as the fundamental lesson learned from 2025 TF and similar events. Detection latency is a tangible reality. We do not detect everything. We miss the majority of objects if they are small, fast-moving, or approaching from an unfavorable direction. The asteroids we successfully detect are those that adhere to predictable patterns, arriving on expected trajectories from known directions at anticipated times. Those that deviate from these norms, the unpredictable ones, are the source of our apprehension precisely because they are the ones we fail to detect. Moving forward, our discussion will shift to the question of how comets can pose a threat even without direct impact, exploring how their debris trails and dust clouds create persistent hazards long after the parent object has traversed the region. Part 7 addresses comet fragmentation and the hazard posed by dust trails, presenting realistic speculative scenarios. Even if a comet misses Earth entirely, its dispersed debris can still inflict damage. Let me elucidate the mechanism behind this phenomenon. Comets are not solid, monolithic bodies. They are loosely aggregated structures composed of ice, dust, rock, and organic compounds, held together by weak gravitational forces and surface tension. This composition renders them inherently fragile. As they approach the sun, thermal stress causes them to fracture. Outgassing creates internal pressure that can lead to their disintegration. Tidal forces, exerted when a comet passes sufficiently close to a massive celestial body, can also tear them apart. In some instances, fragmentation occurs subtly, shedding small pieces. In others, it is a spectacular event, breaking the comet into dozens of fragments. Comet Shoemaker-Levy 9 serves as a notable historical example. In 1992, it passed too close to Jupiter and was disintegrated by the planet's powerful tidal forces. The resulting fragments, numbering over 20, spread out along its orbital path. 2 years later, they impacted Jupiter sequentially, generating colossal explosions observable even from Earth. Each impact unleashed energy comparable to millions of nuclear bombs, leaving persistent atmospheric scars on Jupiter for months. This event was both awe-inspiring and a stark demonstration of cometary fragility and the potential danger posed by their fragments. Another pertinent example is Comet 73P Schwarzmann-Wachmann. This comet has undergone multiple fragmentation events. In 1995, it broke into several pieces, and in 2006, it fragmented again, this time into dozens of smaller chunks. Astronomers observed in real time as the comet disintegrated, with each fragment developing its own coma and tail. These fragments continued to disperse, each following a subtly different trajectory. Over time, they coalesced to form a debris stream, a flow of ice and dust tracing the original orbital path. Earth has intersected portions of this stream, resulting in a temporary increase in meteor activity. While not catastrophic, these occurrences were noticeable. Now, let us apply this understanding to R2. The comet has already experienced at least one outburst, indicating inherent instability. If it undergoes fragmentation, the resulting pieces will diverge. The rate of divergence is contingent upon the relative velocities of the fragments, which are directly related to the energy released during the fragmentation event. A gentle separation results in slow dispersal, while a violent explosion leads to rapid divergence. Regardless of the speed, the fragments, along with the dust they generate, will spread out over time. Dust itself represents a significant hazard. Every comet continuously sheds dust as its ices sublimate. These dust particles are minuscule, typically measuring from microns to millimeters in size, yet they travel at speeds of tens of kilometers per second. At such velocities, even a grain of sand possesses substantial kinetic energy. If a dust particle strikes a spacecraft, it can penetrate the hull. If it impacts a satellite, it can damage solar panels, sensors, or communication systems. If it strikes an astronaut during a spacewalk, the consequences could be fatal. The International Space Station, for instance, is equipped with shielding designed to protect against micrometeoroids. This shielding consists of multiple layers engineered to vaporize incoming particles before they can breach the hull. However, these shields are not infallible. Larger particles, or those arriving at unusual angles, can bypass the protective layers. The ISS has sustained multiple impacts, most resulting in minor damage, though some have necessitated repairs. A dense meteoroid stream, such as one generated by a fragmenting comet, considerably elevates the risk. Now consider the geometric aspect. R2's moid is 7 million kilometers, defining the minimum separation between the comet's orbit and Earth's orbit. If the comet fragments and the resulting fragments disperse along its orbital path, some may drift closer to Earth's path. They may not reach zero separation, nor cause an impact, but they will move closer. If Earth happens to pass through this debris stream at an unfavorable time, we could encounter a significantly higher flux of particles. This could manifest as an intensified meteor shower, cause damage to satellites, or lead to micrometeoroid impacts on spacecraft. The probability of any individual particle striking a specific target is low, given the vastness of space and the relative smallness of potential targets. However, the aggregate probability, the likelihood that something somewhere will be impacted, is elevated. We currently have a substantial number of objects in orbit, including thousands of satellites, space stations, and various other spacecraft, all of which are potential targets. Additionally, there is the scenario of atmospheric interaction. If Earth traverses a dense dust stream, even composed of small particles, the cumulative effect might be discernible. There could be an increase in high-altitude airglow or a spike in bolide activity, bright meteors that detonate in the upper atmosphere. Amateur astronomers would likely notice such phenomena, and meteor cameras would record anomalies. While not catastrophic, these events would be unusual, and unusual occurrences tend to trigger alerts. The genuine concern lies not with the dust we can observe, but with the fragments we cannot. A boulder-sized chunk, approximately 1 to 2 meters in diameter, traveling at 30 kilometers per second, would be virtually invisible until it was too late for any effective action. Optical surveys might detect it, but only if they were fortuitously directed at the precise patch of sky at the exact moment of its passage. If the fragment approached from the direction of the sun, it would be imperceptible. If it possessed a low albedo, indicating a dark surface, it would be exceedingly difficult to spot. And if it impacted the atmosphere directly over a populated area, the result could be comparable to or even exceed the Chelyabinsk event in severity. Estimating the probability in such a situation is challenging. We do not know if R2 has already fragmented, nor if it will fragment in the future. We lack information regarding the potential number of fragments, their distribution along the orbit, their size distribution, their velocity distribution, or their trajectory distribution. Our only concrete data is the parent comet's orbital path and the 7 million kilometer separation between that path and Earth's trajectory. Within these constraints, we can assert that the probability of a fragment impacting Earth is low. However, low is not equivalent to zero, and when the consequences of miscalculation are measured in human lives and critical infrastructure, a low probability may not be sufficiently reassuring. Visualization provides further clarity. Again, imagine the comet's orbital path as a thread suspended in space. Now, envision that thread fraying, splitting into dozens or hundreds of finer threads, each following a slightly divergent course. Some of these threads will remain close to the original trajectory, while others will drift away. Over time, this collection of threads expands, forming a diffuse ribbon along the orbital path. Earth's orbit represents another thread, intersecting this ribbon at an angle. For the majority of the time, Earth passes through empty space, but on occasion it crosses the ribbon, and as it does, the particles within the ribbon rain down. This is not mere speculation. It is a phenomenon with historical precedent. Meteor showers are precisely this, streams of debris originating from comets. The Perseids, the Leonids, the Orionids, all are evidence of Earth traversing such debris streams. Every year, Earth encounters these streams, and we witness meteors. Typically, these events are harmless, occasionally spectacular, and very rarely dangerous. In 1833, the Leonid meteor storm produced tens of thousands of meteors per hour. Eyewitness accounts describe the sky as engulfed in fire. If such an event were to occur today, with our extensive satellite infrastructure, the resulting damage would be severe. R2 is not predicted to generate a meteor storm. Its debris, if present, is likely too sparse. However, we cannot be certain until we observe it directly, and by the time we can observe it, it may be too late to take any action other than to witness the event unfold. Our next inquiry will address a broader question. Are we witnessing an increase in unexpected celestial visitors? Or is this merely a consequence of observational bias? Is the solar system genuinely sending us more objects, or are we simply becoming more adept at detecting them? Part 8 explores pattern recognition and addresses the question, are we seeing a surge of surprise visitors? Allow me to list some examples. Oumuamua arrived in October 2017, marking the first confirmed interstellar object detected passing through our solar system. Its characteristics were unusual, elongated in shape, tumbling erratically, and exhibiting acceleration patterns that did not align with standard outgassing models. It vanished before we could properly examine it. Then, in August 2019, Borisov arrived, our second visitor from beyond the stars. This one was unmistakably a comet, complete with a discernible coma and tail, its composition aligning perfectly with our expectations of interstellar debris. Now we have 3 Atlas, discovered in 2025, yet another object not originating from our solar system. This one, depending on your viewpoint, is either an asteroid or the nucleus of a comet. Its color fluctuates. It's peculiar. And as the world's attention is fixed on 3i Atlas, R2 quietly slipped in from our own cosmic neighborhood, going completely unnoticed until after it passed its closest point to the Sun. That's 4 celestial bodies in 8 years: Oumuamua, Borisov, 3 Atlas, and R2, each with a different origin, distinct composition, and unique discovery circumstances, yet all of them unforeseen. Every single one arrived with little to no prior warning. Could this be a trend? Is this a surge in arrivals? Or is it simply a consequence of us finally paying closer attention? There are 3 leading theories. The first posits an observational bias. Our instruments have improved significantly. We have more sophisticated telescopes, broader sky surveys, and an increasing number of amateur astronomers equipped with data comparable to professional standards. Our search has intensified, leading to more discoveries. Survey systems like Pan-STARRS and the forthcoming Vera C. Rubin Observatory are specifically designed to detect ephemeral events, moving objects, and anything that exhibits change. As these systems become operational and refine their capabilities, the rate of detection will naturally increase. This doesn't necessarily imply an increase in the number of objects arriving, but rather that we are now capable of seeing objects that have always been present. The second hypothesis suggests a genuine increase in the dynamical flux. Perhaps an external factor is unsettling the Oort cloud. It's conceivable that a passing star, long since departed, sent a wave of comets inward, and we are only now witnessing the initial arrivals. It's also possible that our solar system is traversing a region of space with a higher density of cosmic debris. Galactic tides, the gravitational influence of the Milky Way's structure, could be nudging more comets toward the inner solar system. This scenario is not implausible. The Oort cloud is vast, estimated to contain trillions of comets. Even a minor disturbance could propel thousands of them inward over the span of a few thousand years. From our limited human perspective, accustomed to short timescales, this might appear as a sudden influx. The third theory points to statistical clustering. It suggests pure coincidence. Random processes, by their nature, can produce clusters. If you toss a coin 100 times, you're likely to observe streaks of heads or tails. This doesn't indicate a biased coin, it simply demonstrates that randomness can manifest in clumps. 4 unexpected visitors in an 8-year period might merely be statistical noise, a fluctuation without any underlying significance. In another 8 years, we might observe none, or conversely, as many as 10. Without additional data, differentiating between a genuine signal and random noise remains challenging. Each hypothesis is supported by some evidence. The argument for observational bias is particularly strong. The number of known near-Earth asteroids has dramatically increased over the past 2 decades, not because more asteroids have suddenly appeared, but because we initiated a systematic search for them. The same likely applies to comets. The Solar and Heliospheric Observatory, SOHO, has discovered thousands of comets, many of them sun grazers, simply because SOHO possesses observational capabilities that optical telescopes lack. As our detection network expands, so does our catalog of discoveries. However, observational bias alone doesn't account for all anomalies. Oumuamua, for instance, was genuinely perplexing. Its elongated shape, its non-gravitational acceleration, and its conspicuous absence of a visible coma defied straightforward explanations. Some astronomers speculated it was a fragment of a planet shattered by tidal forces in another star system. Others proposed it was an iceberg of hydrogen or nitrogen, a shard of frozen gas. The explanations became increasingly exotic because the simpler ones didn't fit the observed data. And then it departed, leaving us without the opportunity for further study. 3A Atlas also presents peculiarities. Its color seemed to shift from red to green, or so it appeared depending on which observations one trusts. Asteroids typically do not exhibit such color changes. Color is a direct indicator of surface composition. A change in color suggests a transformation in composition, implying that the surface is not uniform. Perhaps it rotates, with different sides reflecting distinct wavelengths of light. It's possible it's subtly outgassing, with the resulting coma influencing the observed spectrum. Or it could be something else entirely. We simply don't know, as we haven't been able to get close enough to resolve it definitively. R2, in its own way, fits the emerging pattern. It is not an interstellar visitor, it is native to our solar system, likely originating from the Oort cloud. However, it remained hidden in the sun's glare, only becoming visible after its perihelion passage. This incident highlights how easily we can overlook objects, even within our immediate cosmic vicinity. If R2 can elude detection, so can others. How many long-period comets traverse the inner solar system annually without being detected? We lack this knowledge. We only observe those that become sufficiently bright, remain visible for an adequate duration, and cross our detection thresholds. The rest remain unseen. Is there a discernible pattern? Perhaps. The optimistic interpretation is that we are becoming more adept at perceiving the universe as it truly is, teeming with transient visitors, streams of debris, and unexpected arrivals. The pessimistic view suggests that the rate of these arrivals is escalating, and we are ill-prepared. The most probable interpretation likely lies somewhere between these two extremes. We are indeed discovering more because our observational efforts have intensified. However, we are also learning that the baseline rate of cosmic traffic is higher than we previously estimated. Our solar system is not a tranquil locale. It is a busy thoroughfare, and we are just now beginning to install the necessary surveillance systems. In the subsequent segment, we will examine the institutions responsible for managing this cosmic traffic, exploring the data pipelines, the bottlenecks, and the silences that fuel public suspicion. This brings us to Part 9, Institutions, Silence, and the Information Life Cycle. Allow me to guide you through the process by which a discovery transitions into public awareness. An observer, whether a seasoned professional or an enthusiastic amateur, identifies something unusual, a moving object, a brightening celestial source, or an ephemeral event. They meticulously record its position, the precise time of observation, and its apparent brightness. Subsequently, they ascertain whether the object has already been catalogued. If it is a novel discovery, they submit a report. Where is this report submitted? To the Minor Planet Center, MPC, operated under the auspices of the International Astronomical Union. The MPC serves as the central clearinghouse for observations pertaining to asteroids, comets, and other smaller celestial bodies. It collates data from observers worldwide, rigorously verifies its accuracy, and issues circulars upon confirmation of new discoveries. However, the verification process is inherently time-consuming. A single observation is insufficient for confirmation. Multiple observations are required to establish the object's reality, rule out instrumental anomalies, and calculate a preliminary orbit. This necessitates waiting for other observers to direct their telescopes towards the same region of the sky and corroborate the sighting. If the object is faint, near the detection limit or moving at a high velocity, confirmation can extend for days or occasionally even longer. Once confirmed, the MPC assigns a provisional designation and disseminates an electronic circular. The data is publicly accessible, available to anyone, but it comprises raw observations. This includes orbital elements, positional vectors, and magnitude estimates. It is not a press release nor a sensational headline. It is a technical document intended for the astronomical community. The general public typically does not consult MPC circulars. They rely on news articles. And these articles, if they appear at all, are published later. In the interim, other institutions refine the orbital parameters. The Jet Propulsion Laboratory, JPL, manages the Horizon System, a sophisticated platform for calculating precise trajectories of solar system objects. As more observational data becomes available, the orbital solution improves, uncertainties diminish, and predictions gain greater reliability. If an object is deemed potentially hazardous, particularly if its orbit brings it into close proximity with Earth, JPL flags it. The Center for Near-Earth Object Studies, CNEOS, then evaluates the associated risk. If the risk is deemed sufficiently high, NASA issues a formal statement. If the risk is low, such a statement may not be released. For R2, the process unfolded as follows. Vladimir Bazugi, an amateur astronomer, detected the object in SOHO data on September 11th, 2025. He promptly submitted his findings. Other observers subsequently confirmed it optically. The MPC issued a circular assigning it the designation C2025R2. JPL calculated its orbit, and CNEOS conducted an assessment. The conclusion reached was that it posed no threat. Its closest approach was projected to be 0.26 astronomical units, a distance deemed safe. Consequently, there was no press release, no public alert, merely a technical update embedded within a database. And this is where the silence begins. It's not due to any deliberate withholding of information, nor a clandestine conspiracy, but rather because the system is primarily designed for risk mitigation, not for public engagement. Objects that do not pose a threat do not typically generate headlines. And when they don't make headlines, the majority of people remain unaware of their existence. R2 received mentions in a handful of astronomy-focused publications and a few space news websites. It was featured as the Astronomy Picture of the Day on September 18th. However, it did not trend on social media, nor did it dominate the news cycle. It was simply another comet, one among dozens discovered annually. Contrast this with the interstellar object 3 Atlas. Mysterious, exhibiting color changes, and displaying peculiar acceleration. That is the stuff of headlines. That is the kind of narrative that captivates mainstream media, goes viral on social platforms, and sparks discussions in online forums. The fact that 3 Atlas is harmless, that its closest approach will be 1.8 astronomical units, posing no direct risk, is secondary. What matters is its inherent fascination, and fascination sells. This situation creates a void when institutions fail to provide timely and accessible updates. When the information life cycle is slow and technical, when the gap between discovery and public awareness stretches to weeks or even months, speculation inevitably fills the void. Social media users notice these information gaps. They raise questions. Why aren't we hearing more about this? Why is the coverage so limited? Is something being concealed? And in the absence of official explanations, unofficial ones emerge: theories, conspiracies, and rumors. Vladimir Bazugi's discovery of R2 serves as an instructive example here. He is not a professional astronomer. He does not work for a space agency. He is an amateur who possesses the skills to analyze SOHO data. The fact that he identified the comet before the professional surveys did is not a reflection of failure on the part of the professionals. It serves as a potent reminder that the detection network is not impenetrable, that non-traditional avenues of discovery are significant, and that sometimes the most crucial observations originate from unexpected sources. However, It also raises further questions. If an amateur can discover a comet that eluded professional surveys, what else are we missing? How many objects traverse the inner solar system undetected simply because they are in the wrong place at the wrong time? This could be due to surveys focusing on other celestial regions, unfavorable sky conditions, or instrument downtime for maintenance. We do not know. We cannot know. And that is the fundamental problem. The information life cycle is deliberately protracted. Verification procedures are in place to prevent false positives. Caution is exercised to avert public panic. However, this same caution also creates information gaps, and these gaps breed doubt. When individuals lose trust in institutions to provide accurate information, they seek out alternative sources, and these alternative sources are not always reliable. Next, we will shift our focus to a critical assessment of unconventional ideas, conspiratorial claims, and fringe theories. We will endeavor to distinguish between those that warrant serious consideration and those that do not. This leads us to Part 10, Wild Cards and Conspiracies. Let me be explicit. Some will assert that R2 is not a natural celestial body. They will propose it is a probe, a craft, or an engineered device dispatched by some entity to observe us. They will argue that its trajectory is too perfectly aligned, its timing too precise, and its outburst too controlled. They will claim that NASA possesses more information than it is divulging, that photographic evidence is being suppressed, and that the genuine data is classified. They will interpret it as a message, a warning, or a test, and they will firmly believe these assertions. Therefore, let us undertake a triage of these claims, examining each one individually to ascertain which, if any, merit any degree of attention. Claim 1. R2 is an artificial object. Is this physically plausible? In principle, yes. Any sufficiently advanced civilization could construct a spacecraft designed to resemble a comet. They could coat it in ice to create a coma when exposed to heat. They could program it to emit outbursts on a predetermined schedule. They could engineer its trajectory to pass close to Earth. While possible, this is not a simple feat and would inevitably leave detectable traces. If R2 were artificial, we would expect to observe anomalies. Spectroscopic analysis would likely reveal unusual compositions, elements, or molecules that deviate from the typical chemistry of natural comets. The nucleus might exhibit structural features, geometric shapes, or regular patterns absent in natural objects. The trajectory might display fine-tuned adjustments, minute corrections inconsistent with simple outgassing, and there would likely be electromagnetic emissions, such as radio signals or infrared signatures, indicating active systems. To date, we have not detected any such evidence. The spectrum appears consistent with that of a normal comet. The coma's behavior is explicable by sublimating ice. The trajectory adheres to gravitational dynamics. There are no detectable signals of artificial origin. Occam's razor suggests that the simplest explanation is typically the correct one. R2 appears to be a comet because it is, in all likelihood, a comet. To invoke an artificial origin requires introducing additional assumptions, increasing complexity, and positing actors with unknown motives and capabilities. It is conceivable, but not essential. And in the realm of science, we refrain from introducing unnecessary explanations. Claim 2. The images are being suppressed. Are we privy to all available visual data? Almost certainly not. Professional observatories do not publish every single image they capture. They engage in data processing, calibration, noise filtering, and the selection of the most optimal frames. Some data is proprietary, reserved for the specific research teams that proposed the observations. Other data may be of low quality and thus not deemed worthy of release. However, suppression implies deliberate intent, a coordinated effort to conceal information. Such an undertaking would necessitate a level of coordination that is exceedingly difficult to achieve. Observatories are geographically dispersed and operate independently. Amateur astronomers possess their own equipment. If a truly dramatic visual phenomenon were occurring, someone would undoubtedly make it public. The absence of spectacular images suggests that none exist to be seen, rather than implying that they are being hidden. Claim 3. The trajectory is being manipulated. Could an external force be steering R2? If by external force you refer to extraterrestrial intelligence, then we are returning to Claim 1. If, however, you mean natural forces, then yes. Outgassing, the release of volatile materials, creates non-gravitational accelerations. Comets do not follow purely ballistic paths. They exert their own propulsion by venting gas. R2 has exhibited outbursts, indicating that it is venting material, which in turn affects its trajectory. JPL's orbital models incorporate these non-gravitational forces, accounting for outgassing. While trajectory predictions are not perfectly precise, they are generally accurate. If the comet were under active control, we would expect to observe deviations from these models that could not be explained by outgassing alone. We have not witnessed such deviations. Claim 4. This is harmless but symbolic. Some individuals contend that even if R2 poses no immediate threat and will not impact Earth, its arrival carries significance, serving as a sign, a portent, or a synchronicity. This is not a scientific assertion, it is a philosophical or spiritual one. Science can delineate an object's orbit, its composition, and the probability of impact. It cannot, however, determine whether the universe is conveying a message, as this falls outside the purview of empirical inquiry. If you derive personal meaning from the arrival of a comet, that is your prerogative. However, it is crucial not to conflate personal interpretation with physical risk. Now, are there any claims that warrant more detailed examination? Yes. One such claim pertains to the potential for fragmentation and the associated debris hazards, which is a real physical possibility. This is not a conspiracy theory. It is grounded in physics. If R2 were to fragment or shed pieces that deviate from its primary trajectory, these fragments could indeed pose a hazard. While an impact hazard is improbable, a debris hazard, such as an increased micrometeoroid flux or a threat to satellites, is plausible and certainly warrants monitoring and preparation. This is speculative, but it is based on our understanding of cometary behavior. The triage matrix can be summarized as follows. Artificial origin is not feasible without supporting evidence. Image suppression is unlikely given the distributed nature of astronomical observation. Trajectory manipulation is unsubstantiated beyond natural outgassing phenomena. Symbolic meaning falls outside the domain of scientific inquiry. Fragmentation and debris are plausible scenarios that merit continued tracking. Speculation is an enjoyable and inherently human pursuit. It is natural for us to perceive patterns, to imagine agency, and to fill informational voids with narratives. However, we must always be prepared to test these narratives against empirical data. And when the data fails to support a particular narrative, we must possess the discipline to set that narrative aside and proceed. Next, we will transition to a different subject matter, exploring other recent developments in scientific headlines. We will begin with neuroscience, as the brain itself functions as a detection system, complete with its own inherent blind spots. This leads us to Part 11, Neuroscience. In August of 2025, researchers at the University of California, San Francisco, UCSF, published findings detailing a protein that appears to play a role in regulating the aging process of the brain. Identified through experiments conducted on aged mice, this protein seems to act as a brake on neural plasticity. When the researchers inhibited this protein's activity, the aged mice demonstrated improvements in memory and learning capabilities. Their neurons exhibited more reliable firing patterns, and their synaptic connections became stronger. By some metrics, their brains functioned akin to those of younger mice. The experimental design was straightforward. Take aged mice, identify the protein that accumulates with age, neutralize its activity using a pharmacological agent or genetic manipulation, and then assess whether behavioral improvements occurred. The results were encouraging. Aged mice that underwent the treatment performed better on memory-related tasks. They navigated mazes with greater speed and recognized objects more consistently. The effects were measurable, repeatable, and statistically significant. However, it is crucial to remember that these are findings derived from mouse studies. Mice are not humans. Their brains are simpler, smaller, and organized differently. What proves effective in a mouse does not always translate to humans. The history of neuroscience is replete with examples of treatments that successfully cured mice but failed during human clinical trials. Alzheimer's disease, for instance, has been effectively cured in mice on numerous occasions, yet humans continue to await a breakthrough. Therefore, caution is paramount. While the findings are exciting, they remain preliminary. The potential implications, should they prove transferable to humans, are enormous. Cognitive decline is among the most feared aspects of aging. Memory loss, diminished learning capacity, and slowed processing speed all impact independence and self-identity. If inhibiting a single protein could effectively slow or even reverse this decline, the societal impact would be profound, not only for individuals but also for societies grappling with aging populations. The global economic burden of dementia is measured in trillions of dollars. A treatment that could delay its onset by even a few years would yield substantial savings in resources and alleviate immense suffering. However, challenges remain. Proteins do not operate in isolation. They are integral components of complex networks, cascades, and feedback loops. Inhibiting one protein could have unforeseen downstream effects, potentially disrupting other bodily systems. While the aged mice in the study did not exhibit overt side effects, the observation period was relatively short. Long-term consequences are currently unknown, and human biology is considerably more complex. Humans live longer lives, accumulate more physiological damage over time, and often have multiple coexisting health conditions. A treatment that functions seamlessly in a mouse might interact unpredictably with human physiology. Consider this analogy. The brain functions as a sophisticated detection system. It continuously scans the environment, processes incoming signals, forms memories, and generates predictions. When operating optimally, it discerns intricate details and adapts effectively. As the brain ages, its sensitivity diminishes. Signals weaken, background noise increases, and the ability to recognize patterns becomes more challenging. The protein identified by the UCSF researchers appears to be implicated in this degradation process. By inhibiting its activity, the researchers were able to restore some of the brain's youthful sensitivity. Now, let us draw a parallel to our astronomical detection systems. Telescopes scan the celestial sphere, process incoming light signals, catalog celestial objects, and predict their trajectories. When functioning optimally, they can detect faint comets, track asteroids, and provide warnings of potential hazards. However, these systems too are subject to degradation. Instruments age, sensors drift, calibration accuracy decreases, and data pipelines can become cluttered with noise. Over time, we begin to miss phenomena that we were once capable of detecting. While the analogy is not perfect, it offers valuable insight. Both systems, the brain and the telescope, are designed to identify patterns within noisy environments. Both are susceptible to degradation over time, and both, to some extent, can be restored through intervention. For the brain, this intervention might involve a protein inhibitor. For telescopes, it could entail recalibration, sensor replacement, or the implementation of upgraded algorithms. The underlying principle remains consistent. Maintaining vigilance requires ongoing maintenance. The UCSF study serves as a crucial reminder that unseen processes govern our perception, dictating what we notice and what escapes our attention. These processes can be biological, such as the accumulation of proteins as we age, or technological, like a misaligned sensor. They can also be institutional, like survey schedules with inherent gaps. Regardless of the cause, the remedy follows a consistent pattern: identify the underlying mechanism, comprehend its functionality, and then implement an intervention to restore proper operation. Subsequently, we will examine another significant finding in neuroscience, this time focusing on Alzheimer's disease. Understanding the recurring cycle of sensational pronouncements, followed by tempered realities in this field, is particularly valuable. This segment, Part 12, delves into a headline concerning the reversal of Alzheimer's. The month of October in the year 2025 brought a fresh wave of prominent headlines proclaiming Alzheimer's reversed in mice. The accompanying articles conveyed in breathless excitement, and social media posts radiated hope. However, the actual situation was considerably more intricate. Researchers had been evaluating a novel intervention, potentially involving the restoration of vascular function, the clearance of amyloid proteins, or the regulation of protein accumulation. While the specific details differed across various studies, a common thread emerged. Aged mice exhibiting cognitive impairments demonstrated improvements following the treatment. Their brains showed reduced plaque buildup, their memory recall enhanced, and in some quantifiable aspects, the disease's pathological indicators reversed. This is not an unprecedented occurrence. For the past 2 decades, Alzheimer's research has yielded a multitude of promising studies conducted on mice. These have included vaccine strategies designed to eliminate amyloid, pharmaceutical interventions to diminish tau tangles, and gene therapies aimed at re-establishing synaptic function. While these approaches have proven effective in murine models, the vast majority have ultimately failed when translated to human trials. The disparity between preclinical results and human outcomes is immense. Mouse models of Alzheimer's do not fully recapitulate the complexities of the human disease. Mice have significantly shorter lifespans, precluding the development of the full spectrum of Alzheimer's pathology. Their brains possess simpler structures, their immune systems differ, and their metabolic rates are considerably faster. Consequently, a therapeutic agent that proves beneficial in a 6-month study with mice might prove ineffective in a decade-long human clinical trial. Sample sizes are a critical factor. Mouse studies frequently involve only a few dozen animals, whereas human trials necessitate thousands of participants. The duration of study is also paramount. Mouse studies are typically conducted over months, while human trials span years. Potential side effects carry substantial weight. A drug deemed safe in mice might exhibit toxicity in humans. Similarly, efficacy is a key consideration. A treatment that enhances memory by 20% in mice might only yield a 5% improvement in humans, and such a marginal gain may not be clinically significant. The summary presented by Newsweek, much like many popular science articles, strategically highlighted the positive aspects: reversal, breakthrough, hope, elements that are highly marketable. In contrast, the primary research papers, the actual source documents, adopted a far more reserved tone. They employed phrases such as preliminary, limited, and requires further study, explicitly acknowledging the challenges of translating findings and refraining from claiming definitive success, instead reporting progress. The fundamental issue lies in the transformation of complex scientific findings into sensational headlines, leading to the erosion of nuance and the eradication of uncertainty. This widening chasm between the researchers' actual discoveries and the public's understanding of those discoveries creates a disconnect. Consequently, when a treatment ultimately proves ineffective in humans, or when clinical trials yield negative results, the public often feels deceived, having been promised a cure, and instead facing another disappointment. This erosion of trust is a predictable outcome. This pattern is not exclusive to Alzheimer's research. It is observable across all scientific disciplines where high stakes and intricate subject matter are involved, including cancer research, climate science, infectious disease studies, and indeed, astronomy. When a new comet is identified, headlines often herald spectacular celestial displays, events described as once in a lifetime or visible to the naked eye. However, the reality is frequently less brilliant, more uncertain, and subject to variables beyond our control. Comets can dim, fragment, or simply fail to meet expectations. The public, anticipating a grand spectacle, can then feel let down. The appropriate response to such situations is not cynicism, but rather skepticism. Maintain skepticism. When confronted with a headline proclaiming a scientific breakthrough, make an effort to consult the original research paper. Scrutinize the sample size, identify any caveats, and question precisely what the researchers measured and what they inferred. Inquire about the limitations of the study and the planned next steps. Most of the time, the answer will involve a call for further research, which is entirely appropriate and fundamental to the scientific process. However, this contrasts sharply with the nature of headlines, which typically demand certainty, while science operates primarily on probabilities. The parallel to R2 is this. The comet is a tangible entity, the observations are factual, and the orbit calculations are accurate. However, predictions regarding its brightness, potential fragmentation, and ultimate trajectory are all probabilistic. We do not possess definitive knowledge of future events. Rather, we understand potential outcomes with varying degrees of likelihood. The responsible approach is to present these probabilities clearly, without exaggeration or understatement, and certainly without resorting to sensationalism to drive engagement. Next, we transition to the domain of artificial intelligence. This is another field where the divergence between hype and reality is pronounced, yet it also represents an area where tangible advancements are revolutionizing our capacity to identify cosmic threats. This section, Part 13, addresses AI model and tool releases, as well as the ethical considerations that accompany them. The month of October in the year 2025 witnessed a series of significant announcements in the realm of artificial intelligence, including the unveiling of new models, tools, and enhanced capabilities. Open-source releases pushed the boundaries of what machine learning could achieve, introducing foundational models with improved reasoning abilities, superior context management, and faster processing speeds. Both commercial enterprises and research laboratories introduce systems capable of handling extensive contexts, maintaining coherence across intricate reasoning processes, generating code with greater reliability, and interacting with multiple sensory inputs simultaneously. The pace of development is exceptionally rapid. What was considered inconceivable just 2 years prior has now become commonplace, and what is routine today is likely to be outdated within the next 2 years. This acceleration is tangible, measurable, and shows no signs of abating. Concurrent with this technical advancement, a strong ethical push emerged, with initiatives aimed at aligning AI development with human values gaining momentum. These efforts, often presented at global forums and supported by researchers and policymakers, acknowledge the immense power and accelerating progress of AI. The overarching objective is to ensure that AI's trajectory is aligned with our genuine desires, not merely our perceived wishes, particularly when consequences become tangible. The critical question is not solely about AI's capabilities, but about its ethical applications and the individuals or groups responsible for its direction. These are not abstract philosophical inquiries, but urgent practical concerns. As AI systems become increasingly sophisticated, autonomous, and integrated into vital infrastructure, the stakes escalate. Errors in medical diagnostics can have fatal consequences. Mistakes in traffic management can lead to accidents. In astronomical detection, a lapse could render us vulnerable to undetected incoming threats. In astronomy, AI is already an integral component of data processing pipelines, a reality rather than a speculative future. Automated anomaly detection systems actively scan survey images for transient phenomena. Machine learning algorithms classify celestial objects, differentiating between asteroids and stars, comets and galaxies, and supernovae and variable stars. These classifications occur within milliseconds, a task that would require humans minutes or even hours to complete. Algorithms are employed to refine orbital calculations, processing sets of positional measurements to determine trajectories. They predict future positions, estimate uncertainties, and flag objects whose paths bring them into proximity with Earth. These systems identify potential hazards, objects that may pose collision risks, necessitate follow-up observations, or require addition to watch lists. The sheer volume of data generated by modern wide-field astronomical surveys is too immense for manual human processing. These surveys can produce terabytes of data each night, with each individual image containing millions of sources. Each source must be meticulously measured, cataloged, and cross-referenced with existing databases. Transient events, phenomena that appear, disappear, or change in brightness, must be identified and flagged. The Vera C. Rubin Observatory, upon becoming fully operational, will image the entire visible sky every few nights, detecting billions of objects. Tens of thousands of these will be in motion, exhibiting change, or appearing as transients. No human team could possibly process such an enormous quantity of information. AI is indispensable for sifting through this data and discerning signals embedded within the noise. Without AI, contemporary astronomy would be overwhelmed by its own success, inundated by the sheer volume of information acquired by telescopes nightly. However, AI is not infallible. It is prone to errors. It can generate false positives, identifying objects that appear hazardous, but are not. For instance, a cosmic ray striking a detector might create a bright streak, which the AI might interpret as a fast-moving object and flag as a potential asteroid. Subsequent observations would reveal nothing, indicating the object was an artifact, a glitch, or a phantom. Alternatively, the AI might misclassify objects. A distant supernova that brightens gradually might exhibit a light curve resembling that of a variable star, leading the AI to assign it to the incorrect category. Several days might pass before a human astronomer notices the error and corrects the classification, by which point the optimal observation window may have closed, resulting in the loss of critical data. Furthermore, AI can miss genuine signals, particularly if they are unusual or do not align with its training data. Machine learning systems learn by example. By presenting the system with thousands of images of asteroids, it learns to recognize their characteristics. Similarly, exposure to thousands of comets enables it to identify cometary features. However, the system may struggle with objects that deviate from these established patterns. When presented with an object exhibiting properties outside the distribution it was trained on, the AI might classify it as noise, an artifact, or something to be disregarded. Alternatively, it might miscategorize it, diverting it down an incorrect processing pathway. In either scenario, the signal is lost. AI can also perpetuate biases. If the training dataset is skewed towards particular types of objects, the AI's subsequent analyses will also reflect this bias. For example, if the majority of training data consists of objects detected by optical surveys in specific sky regions, observed under particular conditions or at certain times of the year, the AI will learn this pattern. It may learn that asteroids typically fall within certain brightness ranges, possess specific colors, and exhibit particular motion rates. Consequently, an object that deviates from this established pattern, perhaps it is darker than usual, has a lower albedo, reflects less sunlight, moves faster or slower than anticipated, or originates from an unexpected direction, may not be recognized by the AI trained on the biased sample. Such an object might be filtered out, with the system only identifying what it was trained to recognize and overlooking everything else. There is also the issue of the noise flood. As AI becomes more adept at identifying anomalies, it inevitably generates a greater number of alerts. While this might seem beneficial, suggesting improved coverage and fewer missed objects, an increased volume of alerts necessitates more follow-up observations. This, in turn, demands more telescope time, increased human effort, and greater resource allocation. Telescopes are expensive, with time on major observatories costing thousands of dollars per hour. It is impractical to follow up on every single alert. Prioritization is essential, requiring decisions about which objects warrant the investment of resources and which do not. If the rate of false positives is high, the system can become overwhelmed. Astronomers may find themselves dedicating all their efforts to chasing phantom signals, thereby missing genuine threats. Achieving a balance between sensitivity, the ability to detect real signals, and specificity, the ability to reject false signals, is a significant challenge. While the goal is to maximize both, a practical trade-off exists. Increasing sensitivity will capture more genuine objects, but also more false positives. Conversely, enhancing specificity will reduce false positives, but may lead to the omission of some real objects. The optimal balance, where most genuine threats are detected without generating an excessive number of false alarms, is a narrow and constantly shifting target. It is influenced by data quality, observing conditions, and the specific characteristics of the objects being sought. This requires continuous adjustments, ongoing feedback, and constant human oversight. Consider a hypothetical scenario. An AI analyzing data on comet brightness flags an unusual spike in R2's light curve. The comet has been steadily increasing in brightness since its discovery, consistent with rising solar heating as it approaches the sun. However, on October 25th, its brightness abruptly jumps, perhaps by only half a magnitude, but the increase is sharp and sudden, deviating from the gradual change predicted by existing models. This appears to be an outburst, yet its timing is peculiar. The pattern does not align with previously observed outbursts, which typically occurred near perihelion when solar heating was at its peak. This event, however, is happening weeks later, as the comet moves away from the sun, which is highly unusual. The question arises, is this observation real, or is it an instrumental artifact? Perhaps the telescope experienced a tracking error, or atmospheric conditions changed, or the calibration was inaccurate. Alternatively, could it be something unexpected, a physical phenomenon occurring with the comet, such as fragment ejection, a collision with a meteoroid, or the sudden exposure and explosive venting of a volatile gas pocket? The AI, lacking the capacity for physical reasoning or an understanding of comet behavior models, cannot definitively answer this. It merely compares the incoming data to patterns it has previously encountered. Since this particular pattern is atypical, the AI flags the anomaly and forwards it to a human for evaluation. The human astronomer receives this alert, one among dozens. Upon reviewing the data, she observes the spike and then consults other instruments. Have any other observatories recently monitored R2? Are there independent measurements that corroborate the observed brightness change? A search of databases yields no relevant results. The spike is present only in a single dataset, which is indeed suspicious, as artifacts tend to manifest in isolated datasets, whereas genuine events are usually detected by multiple instruments, unless, by chance, Only one telescope was observing at the precise moment of occurrence. She examines the observing log for any issues that night, such as telescope malfunctions, detector problems, or adverse weather. The log indicates scattered clouds and variable seeing, but no significant anomalies. Visual inspection of images taken before and after the spike shows the comet appearing normal, with no obvious structural alterations, no new fragments, and no dramatic brightening in subsequent observations. The spike appears to have been transient, if it occurred at all. It could have been mere noise or perhaps a brief, real event that lasted only a few minutes, insufficient for confirmation by other observers. She reaches a decision. The evidence is ambiguous. While the spike might be real, it is more likely an artifact. Without corroboration or additional data, issuing an alert would be premature. It would entail expending resources, initiating follow-up observations, mobilizing other astronomers, and ultimately, if the spike proves to be insignificant, wasting everyone's time. Consequently, she opts not to issue an alert. The anomaly is logged in the database, marked as unconfirmed, and subsequently set aside. She proceeds to the next alert. The system continues its operation, but what if the anomaly was indeed real? What if the spike indicated fragmentation, with pieces now diverging from the parent trajectory? The human decision, made under conditions of uncertainty and with incomplete data, might have overlooked a significant event. Fragments take time to separate. In the initial hours or days, they remain close to the parent body, making them difficult to resolve, even with high-resolution imaging. By the time they have separated sufficiently to be observed as distinct objects, they may have diverged enough to pose independent threats. In this scenario, the AI, which initially detected the anomaly, is effectively disregarded, not due to human negligence, but because the astronomer followed established protocols, evaluated the available evidence, and made a reasonable judgment. However, reasonable judgments made under uncertainty can sometimes prove incorrect. Over time, humans may develop a distrust of AI alerts due to the prevalence of false positives. This phenomenon, known as alert fatigue, is well documented in fields such as medical diagnostics, aviation safety, nuclear power plant operations, and now astronomy. When alarms sound frequently without tangible consequence, individuals tend to respond with diminished urgency, becoming desensitized or tuning out. They may develop heuristic strategies to filter the perceived noise. For instance, they might decide to only respond to alerts with confidence scores exceeding 90%, or only follow up if multiple instruments flag the same object, or deprioritize alerts originating from older telescopes known for calibration issues. These heuristics are logical. They conserve time and direct resources towards the most promising targets. However, they can inadvertently filter out genuine signals. A real threat, one that truly matters, might possess a confidence score of 85% or be flagged by only a single instrument because that was the only one observing at the opportune moment, or might originate from an older telescope that, despite its age, detected something significant. When such an alert arrives, it might be dismissed as mere noise. The pattern recognition mechanisms that assist humans in managing information overload can, paradoxically, blind them to genuine anomalies. This presents a fundamental challenge in human-AI collaboration. Neither party is perfect. AI excels at speed and data processing, capable of identifying patterns that would elude humans for hours, never tiring and maintaining unwavering focus. However, it lacks contextual understanding and intuition, and it cannot reason about the physical plausibility of an anomaly. Humans, while slower, possess superior cognitive abilities. They understand physics, rely on intuition, and can reason about causality and plausibility. Their limitations lie in attention span, fatigue, and cognitive biases, restricting their capacity to process vast datasets. They tend to miss events occurring outside their immediate focus. The most effective system arises from the complementary strengths of AI and humans. AI handles the volume of data, while humans provide the judgment. The AI scans everything, flags any unusual occurrence, and presents it to humans for evaluation. Humans then examine the flagged items, applying context and intuition to differentiate between genuine signals and noise. This collaborative approach necessitates trust, careful calibration, and robust feedback loops. Humans must trust that the AI is not overlooking critical signals, and the AI must be calibrated to provide informative alerts rather than overwhelming the system. Furthermore, feedback mechanisms are essential, allowing humans to inform the AI of its successes and failures, thereby enabling continuous learning and improvement. Crucially, it requires humans to remain vigilant, avoiding complacency and not assuming the AI will invariably detect everything. The moment humans begin to perceive AI as infallible, as a perfect detector incapable of error, is the moment the system becomes perilous. AI is not infallible. It is a powerful but inherently limited tool that requires human oversight for optimal functioning. The real danger lies not in AI's potential for failure, but in humanity's tendency to place excessive trust in it, leading to a lapse in attention. When attention wanes, overlooked elements begin to multiply. Detection is no longer solely a matter of hardware. Building larger telescopes with superior optics and more sensitive detectors. It has evolved to encompass software, algorithms, decision trees, neural networks, and statistical thresholds. It involves the rules we establish to distinguish between signal and noise, the models we construct to predict trajectories, and the pipelines we design for data processing. All of these are human creations, trained on data selected by humans and deployed within contexts defined by humans. Any inherent biases, gaps, or blind spots are therefore human constructs, choices, whether deliberate or unconscious, embedded within the systems we engineer. AI can enhance our observational reach, but it cannot rectify the fundamental challenge. We are seeking patterns in a universe that remains indifferent to our discovery efforts. The universe does not prioritize our detection capabilities. It does not simplify processes for our convenience. Objects appear from inconvenient directions at inconvenient times and possess inconvenient properties that deviate from our established training data. They may be obscured by the sun's glare, arrive during adverse weather conditions, or fragment unpredictably. Our detection systems, both human and artificial, must adapt to this inherent reality to avoid failure. The challenge extends beyond merely developing superior tools. It lies in fostering enhanced collaboration between these tools and the individuals who utilize them. Next, we will examine another neuroscience study, this one pertaining to spatial memory and aging, which will serve as a metaphor for the degradation of detection systems over time. This is part 14, focusing on the metaphor of instrument and sensor degradation. Stanford researchers published findings on October 3, 2025, detailing the decline of spatial memory in aging brains. Their study involved investigating neurons within the hippocampus, a brain region crucial for constructing cognitive maps of our environment. These maps are not abstract constructs. These are neural frameworks of physical environments, constructed from lived experiences and honed through repeated exposure. In juvenile creatures, these neurons activate reliably when the animal occupies a distinct location. The pattern of activation is exact, unchanging, and repeatable. Neuron A fires when the animal is in corner 1. Neuron B fires when it is in corner 2. This arrangement establishes a mental map, a neurological coordinate system that enables the animal to ascertain its position and chart a course to its desired destination. However, in aging animals, neuronal activation becomes less dependable. Neuron A might fire in corner 1, or it might activate in corner 2, or it might remain inactive. The map becomes indistinct. Locations merge into one another. The animal still comprehends its presence within an area, but that area is ill-defined. Navigation becomes more challenging. The animal hesitates, it retraces its steps, it takes incorrect turns. It eventually reaches its objective, but the journey is inefficient.